In the realm of high-energy physics, we've recently encountered a series of experimental results that are, to put it mildly, perplexing. These come from our study of what's known as quark-gluon plasma. Today, we're going to delve into a theoretical framework that offers a rather novel interpretation of these confounding observations.
And this statement from Maddie Pitcairn truly encapsulates the intellectual puzzle we face. You see, experiments conducted at the Relativistic Heavy Ion Collider, or RHIC, have produced data that simply do not align with our standard model of particle physics. It suggests that some of our most foundational assumptions may require re-examination. So our inquiry will proceed in 5 stages. First, we'll review the empirical data, the anomalies themselves. Then we'll introduce an alternative theoretical lens known as Topological Geometrodynamics. From there, we'll explore its core concepts and finally see how this framework might resolve the initial puzzle.
All right, let's begin with the experimental outcomes from RHIC. What exactly did the researchers find that so profoundly challenged the predictions of quantum chromodynamics, a reigning theory of the strong force?
Well, there are 4 key observations. First, something called jet quenching, where jets of particles lost their energy far more rapidly than expected. Second, the plasma behaved not like a gas of quarks and gluons, but more like a perfect frictionless fluid. Third, and this was quite a surprise, even very massive, heavy quarks were observed to be swept up in this collective flow. And finally, there wasn't a single sharp critical temperature for this phase transition. Instead, researchers observed what they called a bumpy structure. Now, taken together, these findings strongly indicated that a crucial piece of our understanding was missing. So to account for these anomalies, we now turn to a rather different conceptual structure, Topological Geometrodynamics, or TGD. Now, this framework doesn't merely propose an adjustment to the existing model. It suggests a fundamentally new basis for physical reality itself. The central premise of TGD is a reconceptualization of space-time. Instead of viewing space-time as a passive backdrop upon which physical events unfold, TGD envisions it as a dynamic 4-dimensional surface residing within a much larger, higher-dimensional space. The geometry and topology of this surface, its shape, its structure, are what give rise to particles and forces. It is, you could say, a profound ontological shift. And this brings us to the very heart of the TGD-based explanation. The solution it offers is not derived from conventional thermodynamics, but from a rather elegant and abstract field of mathematics, p-adic number theory. Now, this is where the framework becomes truly intriguing. TGD redefines our notions of mass and temperature. The fundamental quantity is not energy, but mass squared. And temperature is no longer a measure of kinetic energy. Instead, it's an abstract mathematical parameter within a p-adic number system that is responsible for generating the masses of elementary particles. It's a completely different way of thinking about these properties. And here we arrive at what is arguably the single most crucial idea within this entire framework. There is a logarithmic relationship between this p-adic temperature and the mass scale. Now, in standard physics, temperature and energy are tightly linearly coupled. But here, the p-adic temperature changes incredibly slowly, even as the corresponding mass scale changes exponentially. And this has truly profound consequences. This table illustrates the direct consequence of that logarithmic dependence. You can see as the mass scale increases exponentially, the associated p-adic temperature decreases only in slow, small, discrete steps. It is a deeply counterintuitive relationship when compared with standard thermodynamics, and it is precisely this feature that holds the key to explaining the RHIC anomalies. This quote neatly summarizes the 2 critical features of the p-adic model. First, that logarithmic dependence we just discussed, and second, because its foundation is number-theoretic, built upon prime numbers, this temperature spectrum is not a smooth continuum. It can only exist at specific, discrete values. So, we have a theory that predicts a discrete spectrum of temperatures. Interestingly, this idea finds a parallel in a known concept from hadronic physics, the Hagedorn temperature. The Hagedorn temperature is, in essence, a theoretical ceiling on temperature. It's a point where adding more energy to a system of hadrons no longer makes it hotter. Instead, that energy is channeled into creating new particles. The system's temperature effectively gets pinned at this maximum value. And here is the crucial identification that TGD proposes. This abstract number-theoretic p-adic temperature is the physical Hagedorn temperature. This is a profound step, as it links the abstract mechanism of mass generation directly to the observable thermodynamics of hadronic matter.
The implication of this identification is both immediate and powerful. Instead of a single critical temperature, TGD predicts an entire hierarchy of them, a discrete ladder of Hagedorn temperatures. Each rung on this ladder corresponds to a specific p-adic mass scale, and this provides a very natural explanation for the bumpy structure observed in the RHIC data. The plasma isn't cooling smoothly. It is cascading down this discrete staircase of temperatures.
Now, with this theoretical apparatus in place, let us return to the original experimental puzzles from RHIC and see how they are reinterpreted through this new lens.
Let's reconsider jet quenching. The standard interpretation is kinetic energy loss through collisions. TGD offers a fundamentally different picture. The jet is not dissipating kinetic energy. It is dissipating mass squared. This is the physical manifestation of p-adic cooling. The particle is literally transitioning down the discrete mass-temperature hierarchy.
And the other anomalies find explanations as well. The perfect fluid behavior is attributed to long-range quantum coherence, which is a natural feature of the TGD framework. And the question of heavy quarks flowing as if they were light? Well, TGD suggests that within this plasma state, all quarks are effectively massless. Their rest mass only manifests after cooling, which allows them to participate effortlessly in the collective flow.
The crucial point, then, is this. TGD posits that the behavior of reality at its most fundamental level is not merely described by mathematics. It suggests that the very properties of physical systems, mass, temperature, interaction, are intrinsically governed by the deep structure of abstract number fields.